Our universe holds more planets than there are grains of sand on every beach. Among that unimaginable number, a special few orbit in the perfect zone for liquid water and possibly life. This is the story of 30 worlds beyond our sun where scientists see that glimmer of potential. By the end, you will know the names and secrets of our galaxy's most promising addresses for alien life. We will visit a planet shrouded in water vapor and another with 7 Earth-sized siblings. What does a world with 3 suns look like, and could a planet made entirely of ocean be a home? The search for life is no longer a fantasy but a real hunt across the stars. Which of these distant shores feels most like a home waiting to be found? Just 4.2 light-years away, a world circles our nearest stellar neighbor. This is Proxima Centauri b, the closest known exoplanet to our own solar system, a discovery that transformed our cosmic backyard. Orbiting the faint red dwarf star Proxima Centauri, this world was found in 2016. A subtle wobble in the star's light betraying the gravitational tug of a hidden companion. At roughly 1.3 times the mass of Earth, it sits squarely within what astronomers call the habitable zone, that delicate orbital band where temperatures might allow liquid water to pool on a rocky surface. Imagine an Earth-sized world so close to us, cosmically speaking, that a future civilization could theoretically reach it. Yet this proximity comes with profound challenges. Proxima Centauri b orbits extremely close to its dim star, completing a full year in just 11 Earth days. This intimate dance likely results in tidal locking, meaning one side of the planet forever faces the searing light of its sun, while the other is plunged into eternal frozen night. The border between these two extremes, a perpetual twilight zone, could be where conditions are just right. Adding to the drama, red dwarfs like Proxima Centauri are notoriously volatile, frequently erupting with massive stellar flares that bathe any nearby planets in deadly ultraviolet and X-ray radiation. These flares could strip away a protective atmosphere over eons, scouring the surface sterile. But hope is not lost. If Proxima b retained a thick enough atmosphere or possessed a global magnetic field like Earth's, it might shield itself and redistribute heat from its day side to its night. Vast oceans could exist, perhaps hidden beneath ice caps on the dark side or circling the planet in that narrow temperate ring. It is a world of extremes and tantalizing possibilities, a rocky question mark hanging in the void next door. What would it be like to stand on that twilight line, beneath the perpetual crimson glow of an alien sun? The promise of a world next door is shadowed by violent flares, but what if a gentler, more stable version existed? A mere 40 light-years from Earth, a star no larger than Jupiter hosts a miniature solar system that redefines the word family. This is the TRAPPIST-1 system, a cosmic matryoshka doll of 7 rocky planets, each roughly the size of our own world, all orbiting closer to their star than Mercury does to our Sun. Among these 7 siblings, one stands out as a jewel of potential, TRAPPIST-1e. Its size and density tell us it is almost certainly a rocky world, a solid foundation for life as we know it. More importantly, it orbits in the very heart of its star's habitable zone, a sweet spot where temperatures could allow for liquid water oceans, lakes, or rivers. Picture standing on the surface of TRAPPIST-1e. The sky above would be a breathtaking spectacle, not just of stars, but of neighboring worlds. The other 6 planets in the system are so close that they would appear as distinct disks, larger and clearer than our moon, some perhaps showing swirling cloud patterns or icy caps. This proximity creates a delicate gravitational dance, where each planet gently tugs on the others, potentially warming their interiors through tidal forces, much like Jupiter's moons are heated. This internal heat could drive volcanic activity and help maintain a global magnetic field, a vital shield against stellar radiation. While its star is also a red dwarf, it is far quieter and more stable than Proxima Centauri, offering TRAPPIST-1e a calmer cosmic environment. The possibility of a thick, life-sustaining atmosphere and vast bodies of water is so compelling that this world is considered one of the absolute best candidates for harboring life ever discovered. It is a top priority for the next generation of space telescopes, instruments that will one day peer at its atmosphere, searching for the chemical fingerprints of oxygen, methane, or other signs of a living world. Could this compact, harmonious system be a cosmic cradle, with not just one but multiple worlds blossoming with life? While TRAPPIST-1e sits in the temperate heart of the zone, its immediate neighbors offer visions of a different kind of paradise. Moving outward from the star, we find TRAPPIST-1f, a world cooled by its greater distance. It resides on the outer, chillier edge of the habitable zone, a position that would typically suggest a frozen wasteland. Yet this world holds a secret that could rewrite its fate. If TRAPPIST-1f managed to hold onto a thick, insulating atmosphere rich in greenhouse gases, something remarkable could happen. That atmospheric blanket could trap just enough of the star's feeble heat to create a stable, global ocean, a single vast sea encircling the entire planet. Imagine a world with no continents, no mountains breaking the surface, just endless, gentle waves under a perpetual deep red twilight. This is the dream of a true ocean planet, a water world where life, if it began, would exist entirely in a boundless aquatic realm. Next in line is the larger sibling, TRAPPIST-1g. This planet is about 1.5 times the size of Earth, and its lower density tells scientists it is likely rich in water and other light materials. It is not just a wet world, it is a candidate for something even more exotic, a Hycean planet. Picture an environment unlike anything in our solar system, a planet shrouded in a thick, global atmosphere of hydrogen, beneath which lies a planet-wide ocean so deep and pressurized it never meets a rocky seafloor. The surface of this ocean would be a scalding hot layer, heated by the atmosphere above, but descend into the abyssal darkness and you might find cooler, more hospitable depths. In these deep, dark waters, life would not rely on sunlight but on chemical energy from the planet's core or from reactions within the ocean itself, much like the ecosystems thriving around hydrothermal vents on Earth's ocean floor. So while TRAPPIST-1f could be a global sea under a familiar sky, TRAPPIST-1g might be a pressure cooker world with a hidden, deep-sea biosphere. Together, they show that within one tiny star system, the recipe for life may have produced not just one, but several wildly different kinds of kitchens. Yet the TRAPPIST worlds are not alone in their perfect placement. 500 light-years away, nestled in the constellation Cygnus, another landmark discovery forever changed our perspective. The Kepler Space Telescope, a tireless cosmic census taker, found a world that made headlines around the globe, Kepler 186f. This was the very first planet we ever confirmed to be both Earth-sized and orbiting comfortably within the habitable zone of a star beyond our Sun. Before this moment in 2014, we knew of gas giants in the zone, or worlds much larger than our own. Kepler 186f was the proof we needed that planets like ours, small and rocky and potentially temperate, were not rare flukes but common features of the galaxy. It circles a star cooler and redder than our Sun, an M-dwarf, completing an orbit every 130 days. At just 10% larger than Earth, its gravity and landscape would feel hauntingly familiar to any future visitor. Standing on its surface, the daylight would be unlike anything on Earth, a perpetual sunset glow bathing everything in dim, crimson light. This raises a fascinating question for alien biology. Could plants or something like them still perform photosynthesis under this ruddy sun? The answer is likely yes, but they would have evolved to absorb different wavelengths of light, potentially coloring their foliage in deep shades of black or violet to soak up every precious photon. The true mystery of Kepler 186f, however, lies in what we cannot yet see, its atmosphere. Is it a thick, Venus-like shroud of carbon dioxide that bakes the surface, or a thin, Mars-like wisp that offers no protection? Or does it hold the perfect balance of nitrogen, oxygen, and trace gases to nurture liquid water and perhaps life? Scientists are actively debating this very point, using models to simulate its climate. Some simulations suggest that with a robust atmosphere and enough water, Kepler 186f could indeed have stable oceans on its surface, a pale red dot shimmering with alien seas. It stands as a quiet pioneer, the first definitive sign that Earth's basic blueprint is written into the fabric of the cosmos. Kepler 452b offers a vision of home that feels startlingly familiar. Discovered by the Kepler telescope orbiting a star almost a perfect twin of our own Sun, this world is the closest thing to an older cousin of Earth we have ever found. Its parent star, Kepler 452, is a G-type yellow dwarf, bathing its planet in a warm, golden light nearly identical to the sunshine we experience here. Even the rhythm of its years would feel normal to us as it completes an orbit every 385 days, a mere 20 days longer than our own calendar. This places it squarely and securely in the middle of its star's habitable zone, a world with the perfect cosmic address for liquid water. But this cousin is a bit larger and more robust. Classified as a super-Earth, Kepler 452b is about 1.5 times the size of our planet. Standing on its surface, you would feel a stronger pull, a gravity roughly twice what we experience. This has profound implications for its environment. A stronger gravity can hold onto an atmosphere more easily, potentially creating a denser, thicker air that could spread heat more evenly across the globe and offer robust protection from cosmic rays. The landscapes might be dominated by lower, flatter mountain ranges under the immense pressure, with weather systems of immense power and stability. The most mind-bending aspect of Kepler 452b, however, is not its size but its age. Its star system is about 1.5 billion years older than our own. Think about that for a moment. If conditions were right on this world, if oceans formed and the chemistry of life began, it has had an extra 1.5 billion years to develop, to complexify, to evolve. On Earth, that span of time takes us from the first simple multicellular organisms all the way to the dawn of human civilization. What kind of intelligence, what depth of culture or understanding could arise in 1 billion additional years of uninterrupted evolution? The silence from that distant, sunlit world is not an answer but an invitation to wonder. A different kind of giant emerges from the cosmic dark, a world built on a scale that defies simple geology. LHS 1140b is not a gas giant, but a super-Earth of astonishing density, a planet so massive and compact that scientists debate if it should be called a mega-Earth. Orbiting a quiet, nearby red dwarf star just 40 light-years away, this world was discovered not by a subtle stellar wobble, but by the clean, crisp shadow it casts as it passes directly in front of its star from our point of view. This transit makes it a jewel for astronomers, as the starlight filtering through its atmosphere, if it has one, can be dissected to reveal its chemical secrets. What they have learned so far is staggering. LHS 1140b is about 1.7 times the size of Earth, but it packs nearly 7 times the mass. That incredible density points to a world made almost entirely of rock and metal, likely harboring a colossal iron core far larger than our own planets. The surface gravity would be crushing, a force several times stronger than Earth's, shaping a landscape of immense pressure and profound stillness. Yet for all its formidable bulk, this mega-Earth orbits within the habitable zone of its remarkably calm and stable star. This presents a fascinating paradox. How could such a dense, rocky world in the temperate zone not be a scorching hellscape or a frozen desert? one compelling hypothesis paints a picture of serene, hidden beauty. LHS 1140b could be a snowball planet, a world entirely encased in a global shell of ice many miles thick. But beneath that frozen crust, kept liquid by heat from the planet's massive radioactive core and the gravitational squeezing from its star, there might swirl a global ocean, dark, deep, and completely sealed from the surface. This subsurface sea would be a sanctuary protected from cosmic rays and stellar flares, with a stable environment that could persist for billions of years. Around hydrothermal vents on that hidden ocean floor, chemistry could simmer and complexify in perpetual darkness, much like in Earth's own deep-sea trenches. It is a vision of life not on the surface, but in a secret interior abyss, thriving under the weight of a world built like a fortress. The search for a temperate Earth twin often leads to stars very different from our Sun. Just 12 light-years away, orbiting one of the smallest and coolest stars ever discovered, is a world that matches our planet's temperature with uncanny precision, Teegardens Star B. Its host star is a dim, ancient red dwarf so faint it was not even discovered until 2003, despite being one of our closest stellar neighbors. This tiny, cool ember emits most of its energy as infrared warmth, and nestled snugly within its gentle glow is a planet that has stunned astronomers. Based on the starlight it receives, scientists calculate that Teegardens Star B has an equilibrium temperature almost identical to Earth's, assuming it has a similar atmosphere. This makes it one of the most Earth-like worlds we know in this fundamental, crucial way. Its Earth Similarity Index, a formula that compares key traits to our own planet, is among the highest ever recorded. If Teegardens Star B possesses an atmosphere with a composition like ours, with nitrogen, oxygen, and some greenhouse gases, then its surface could indeed host liquid water and a remarkably stable, temperate climate. Rivers could flow under a perpetual, deep burgundy sky, but the true wonder of this system lies in the star itself. Teegardens Star is profoundly old, a relic from the early galaxy that has been burning quietly for at least 8 billion years, far longer than our Sun's 4.6 billion-year lifespan. This extreme age and the star's inherent stability offer a breathtaking possibility. If life did emerge on this world, it has had not just millions, but billions of extra years to develop, to experiment, and to complexify in an environment of remarkable constancy. While our solar system was still a chaotic disk of gas and dust, Teegardens Star B may have already been a settled, mature world. What civilizations, what depths of understanding could arise across 8 billion years of uninterrupted history? The silence from this nearby, ancient and perfectly temperate world is one of the most profound questions in the cosmos. But the story of this ancient star does not end with a single, perfect twin. Teegardens Star holds a second world in its gentle embrace, an outer sibling named Teegardens Star C. This planet orbits further from the dim red sun, placing it on the cooler, outer edge of what astronomers call the conservative habitable zone. In simple terms, it receives less stellar warmth, and without some help, its surface would likely be a frozen expanse. Yet this very position opens a door to a different kind of possibility. If Teegardens Star C managed to retain a thick atmosphere rich in certain greenhouse gases like carbon dioxide or methane, something remarkable could occur. That atmospheric blanket could trap enough of the star's feeble infrared heat to create a temperate, potentially life-friendly environment, much like a greenhouse keeps plants warm on a cold day. This makes it a fascinating counterpoint to its inner sibling. Think of them as two experiments running around the same star. Teegardens Star B, closer in, is bathed in more warmth and might resemble a classic Earth-like world if it has a moderate atmosphere. Teegardens Star C, further out, would need a more substantial, insulating atmosphere to achieve similar surface conditions. One could be a world of open water and familiar climates, while the other might be a colder planet warmed from within by its own atmospheric coat. This pair offers scientists a rare and precious opportunity, a natural laboratory for comparative planetology. By studying two worlds of similar size and age, born from the same stellar nursery but occupying different niches in the habitable zone, we could learn fundamental rules about how atmospheres evolve, how climate is regulated, and what factors truly make a planet livable. Do both planets have air, or did one lose it over billions of years? If they both have atmospheres, how different are their chemical recipes? The Teegarden system presents a cosmic comparison, a chance to move from studying single, distant points of light to understanding the full, dynamic story of how planetary families live and change together. A revolution in our search for life arrived not from an Earth-like twin, but from a world utterly alien to our own. K2-18b is a different class of planet entirely, a so-called mini-Neptune nearly 9 times the mass of Earth and over twice its size. Orbiting a cool red dwarf star 110 light-years away, it was initially seen as a fascinating but likely lifeless gas dwarf. Then, in 2019, data from the Hubble Space Telescope revealed something astonishing. For the first time ever, astronomers had clearly detected water vapor in the atmosphere of a planet within its star's habitable zone. This was not a hint or a tentative signal, but a definitive signature of water molecules floating in the alien air of a distant world. The discovery sent shockwaves through the scientific community because K2-18b is nothing like Earth. Its immense size and lower density suggest it lacks a solid, rocky surface like our own. Instead, scientists believe it may be the first known example of a Hycean world, a theoretical class of planets that are hot, covered in a global ocean, and shrouded by a thick, hydrogen-rich atmosphere. Picture a perpetual, planet-wide sea, its surface heated to perhaps hundreds of degrees by the atmospheric pressure and stellar warmth. Below that scalding surface layer, however, the ocean could descend for hundreds of miles into a dark, immense abyss. In those profound depths, pressures would be crushing, but temperatures could eventually stabilize into a range comfortable for liquid water, even if that water is forever isolated from any rocky seafloor. This environment, while hostile to life as we know it on the surface, could be a haven in the deep. The hydrogen atmosphere, combined with the water vapor and tentative signs of methane also spotted by Hubble, creates a chemical soup that, in the right conditions, could fuel biological processes. The discovery fundamentally expanded the search for habitable worlds. We no longer need to look only for pale blue dots like Earth. We must now consider the possibility of life thriving in the global, dark oceans of steamy, hydrogen-shrouded worlds, a form of existence born in pressure and heat, forever hidden beneath an alien sky. If life can find a way there, the galaxy may be far more diverse and far stranger than we ever dared to dream. This detection of water vapor on K2-18b did more than identify a single wet world. It unveiled an entirely new category of potential life-bearing planets. The Hycean world hypothesis, born from this discovery, suggests that some mini-Neptunes are not barren gas balls, but immense, steamy water worlds. Picture a planet with a rocky core, but one utterly drowned beneath a global ocean tens to hundreds of miles deep. Above this endless sea hangs an atmosphere not of nitrogen and oxygen, but of thick, primordial hydrogen, a blanket that traps heat and creates crushing pressures at the surface. In such an extreme environment, the very surface of the ocean would be a scalding, inhospitable layer. Yet descend into the abyssal darkness and a remarkable stability emerges. That deep, global ocean, sealed beneath the atmosphere and possibly capped by a high-pressure ice layer, could maintain liquid conditions for billions of years, completely immune to the freezing or boiling that can plague planets with thinner air. This creates a habitat of surprising promise. In the perpetual dark of that deep ocean, life would not rely on sunlight but on chemical energy. Hydrothermal vents on the submerged seafloor or chemical reactions within the water itself could provide the sustenance for entire ecosystems, much like the bizarre, beautiful creatures that thrive around Earth's own deep-sea vents. A Hycean world offers a single, vast, and stable aquatic environment on a planetary scale, a hidden biosphere of immense volume where microbial life could potentially flourish and even complexify. What makes these alien worlds especially thrilling for scientists is not just their potential for life, but our newfound ability to search for it. The thick, hydrogen-rich atmospheres of Hycean planets are paradoxically much easier for our telescopes to analyze than the thin, Earth-like atmospheres we once thought were essential. Hydrogen expands an atmosphere, making it puffier and more extended, which creates a larger, clearer signal when the planet passes in front of its star. Starlight filters through more air, giving instruments like the James Webb Space Telescope a richer chemical fingerprint to read. Astronomers are now eagerly training Webb on worlds like K218b, searching for more than just water vapor. They are hunting for specific combinations of gases that, on Earth, are almost exclusively produced by life. One such molecule is dimethyl sulfide. On our planet, this pungent compound is emitted in vast quantities by marine phytoplankton, tiny algae that form the base of the ocean's food web. Detecting dimethyl sulfide in the atmosphere of a Hycean world would be a seismic event, a tantalizing hint that something in that global, sunless ocean is not just living but thriving on a planetary scale. So while we once scanned only for pale blue dots, we now peer into the steamy, hydrogen-shrouded skies of alien water worlds, listening for the faint chemical whispers of a biology born in darkness and pressure. Our galaxy's most promising worlds are not always found in solitude. Orbiting a faint red dwarf star just 22 light-years from Earth is a super-Earth that calls a stellar menagerie home. GJ667cc is a world of profound gravitational complexity, for its parent star is not alone. It is part of a triple star system, a cosmic dance where three suns whirl around a common center of gravity. The planet itself orbits the smallest and dimmest member of this trio, a star known as GJ667c. From the surface of this world, the daytime sky would be a spectacle unlike any in our solar system. The primary sun, a dim crimson orb, would hang prominently, while the two other stellar companions would gleam in the distance as incredibly bright, multicolored stars, casting strange shadows and painting the landscape with an ever-shifting palette of light. This complex gravitational environment is surprisingly stable, a testament to the vast distances between the stars themselves. The planet's orbit is tight and quick, a year passing in just 28 Earth days, but it lies perfectly within the star's narrow habitable zone. With a mass about 3.8 times that of Earth, GJ667cc is almost certainly a rocky super-Earth, a solid world of mountains and valleys under its triple suns. The most compelling fact, however, is the energy it receives. Despite its faint host, the planet gets nearly the same amount of stellar radiation as Earth does from our Sun. This balance suggests that, with a suitable atmosphere, its surface temperatures could be remarkably similar to our own. A day there might feel familiar in warmth, even as the sky tells a different story entirely. For any life that might arise, this celestial ballet would dictate the rhythms of existence. Photosynthetic organisms would have evolved to harness light from multiple sources, perhaps going dormant under the glow of one star and awakening under another. The very concept of seasons could be tied not to a tilted axis, but to the complex, luminous dance of its three suns. It is a world where the poetry of the cosmos is written daily across the heavens, a reminder that life, if it is truly tenacious, may find a way even in the most spectacularly complicated neighborhoods. The poetry of triple suns gives way to a story of human perseverance in the cosmic archives. Kepler 1649c is a world that was almost lost to history, a hidden gem buried within the flood of data from the Kepler Space Telescope. When the mission's automated algorithms first scanned the light curves of its host star, they dismissed the subtle, periodic dimming as a false signal, a trick of the data. This Earth-sized planet was filed away, forgotten. But years later, a team of citizen scientists, volunteers sifting through Kepler's old observations, spotted what the computers had missed. With a trained human eye, they recognized the telltale signature of a transiting world, pulling Kepler 1649c back from obscurity. What they revealed was astonishing. Orbiting a quiet red dwarf star about 300 light-years away, this planet is almost exactly the same size as our own, a true Earth twin in dimension. Its year is just 19.5 Earth days long, a tight orbit that places it snugly within the star's habitable zone. The most compelling number, however, is 0.75. That is the amount of starlight it receives compared to Earth, meaning its solar energy budget is only 25% less than ours. In the vast catalogue of exoplanets, this places Kepler 1649c among the very most Earth-like worlds ever found by Kepler in both size and temperature potential. It is a powerful reminder that discovery is not just about powerful telescopes and complex code, but about the irreplaceable spark of human curiosity and pattern recognition. This rediscovered world now stands as a prime target for future observation. Its size and position make it an ideal candidate for atmospheric studies with the James Webb Space Telescope, where scientists will search for signs of water vapor or other life-friendly gases. Kepler 1649c is more than a planet. It is a testament to the collaborative spirit of exploration, proving that sometimes the most important discoveries are not made by machines alone, but by the patient, watchful eyes of those who simply refuse to stop looking. The quiet rediscovery of a lost world reveals how many more might still be hiding in the data. Among the most promising recent finds is TOI 700d, a planet that ticks nearly every box on an astrobiologist's wish list. Discovered by NASA, a transiting exoplanet survey satellite, or TESS, this world orbits a remarkably quiet and stable M-dwarf star just over 100 light-years away. Its star's gentle nature is the first crucial piece of the puzzle, as it lacks the violent flares that plague so many other red dwarf systems, offering its planets a calmer cosmic environment. TOI 700d itself is almost exactly Earth-sized, and its orbit places it squarely in the middle of its star's conservative habitable zone. This was not a tentative maybe. Follow-up observations with other telescopes confirmed it as a bona fide, rocky world with the right temperature for liquid water. But what truly excites scientists are the climate models. Researchers have run sophisticated simulations for this planet, testing a wide range of possible atmospheric compositions, from a thick carbon dioxide shroud to a thinner, Earth-like mix of nitrogen and oxygen. The stunning result is that in most of these scenarios, TOI 700d could maintain stable bodies of liquid water on its surface. In one model, it appears as a cloud-shrouded water world, all ocean under a global overcast. In another, it looks more familiar with continents, ice caps, and a dynamic climate. This resilience across different models makes it an exceptionally robust candidate for habitability. Furthermore, its star is relatively bright for its class, and the planet transits cleanly across its face from our vantage point. This combination makes TOI 700d one of the most accessible and compelling targets for the James Webb Space Telescope. Webb will soon stare at this system not to take a picture, but to capture the starlight filtering through the planet's atmosphere during each transit. That faint smear of light will contain the chemical fingerprints of whatever gases envelop this world, potentially revealing water vapor, carbon dioxide, or even hints of oxygen. It stands as a quiet, nearby test case, a world where theory and observation are about to collide in our search for another living planet. J357d offers a different kind of promise, the chance to one day see another living world as more than a point of light. Discovered by the TESS mission orbiting a quiet star just 31 light-years away, this super-Earth is a heavyweight with a mass at least 6 times that of our own planet. Its year is a long, slow 55 Earth days, a distant orbit that places it on the cooler, outer edge of its star's habitable zone. The amount of stellar energy it receives is comparable to that of Mars in our own solar system, a fact that initially suggests a frozen fate. Yet the potential of GJ357d lies not in its current warmth, but in what it might hold onto. With its substantial mass, this world has the gravitational strength to retain a thick atmosphere, a powerful insulating blanket. If that atmosphere is rich in certain greenhouse gases like carbon dioxide or methane, it could trap enough of its star's feeble heat to create a temperate surface, transforming a Mars-like chill into an Earth-like mildness. Scientists are actively debating its true nature. Is it a massive rocky super-Earth with towering mountains and deep valleys under a dense sky? Or is it a shrouded mini-Neptune, a world with a small rocky core lost beneath a deep global ocean and a thick gaseous envelope? This uncertainty is part of what makes it so compelling for the future. Its host star is relatively bright and nearby, and the planet's wide orbit means it is far enough from the star's glare to be distinguishable. This combination of factors makes GJ357d a prime target for a future generation of space telescopes designed for direct imaging. Instead of inferring its presence from a wobble or a shadow, these powerful instruments might one day block out the starlight itself and capture the faint, reflected glow of the planet directly. We could see it as a pale dot, and by analyzing the colors and spectra of that light, determine the composition of its atmosphere and even map broad surface features. GJ357d represents a future milestone, the moment we move from detecting worlds to truly seeing them, and perhaps glimpsing the first hints of cloud patterns or continents on another habitable shore. The promise of a nearby world we might one day truly see is mirrored by a recent discovery that feels almost within reach. Wolf 1069b is a quiet revelation, a planet that slipped into the catalogue in 2023 and immediately demanded attention. Orbiting a dim red dwarf star a mere 31 light-years away, this world holds a special distinction. Its mass is almost identical to that of our own Earth. In a galaxy filled with super-Earths and mini-Neptunes, finding a true Earth mass sibling nestled in the habitable zone is a rare and precious event. It is a cosmic mirror in terms of raw material, a ball of rock and metal built to the same fundamental scale as our home. Its year is a short 15-day sprint around its cool star, a proximity that almost certainly locks it into a gravitational embrace we call tidal locking. This means one face of Wolf 1069b forever stares into the crimson glow of its sun, a hemisphere of perpetual daylight, while the opposite side is locked in eternal frozen night. Such a condition might seem to doom the planet, creating a blistering desert on one side and an airless ice sheet on the other. Yet climate models tell a more nuanced and hopeful story. If this world has managed to hold onto an atmosphere with a composition and pressure similar to Earth's, something remarkable could happen. The atmosphere would act as a global circulatory system, transporting heat from the scorching dayside across the terminator line and into the frigid darkness. The result would not be two extremes, but a vast temperate region centered on that perpetual twilight zone. Within this area, stretching deep into the dayside, temperatures could be mild enough for liquid water to pool and persist. Imagine standing on that world where the sun never sets but hangs motionless in a burgundy sky, its light warming a landscape of shallow seas or fertile ground that circles the entire planet like a belt. The night side, still cold, might cradle immense ice caps, but the habitable ring in between could be a stable, life-friendly environment for billions of years. At just 31 light-years distant, Wolf 1069b is tantalizingly close, placing it at the top of the list for future telescopes that will attempt to sniff out the chemical signatures of its air. Is that atmosphere there, and if so, does it carry the faint, telltale whispers of water vapor or even biosignatures? This nearby Earth mass twin offers a profound question. Can a world that looks so different in its rhythm still beat with the same potential for life? The search for life often leads us to siblings, worlds born from the same stellar nursery yet destined for different fates. Over 1,000 light-years away, orbiting a star older and dimmer than our Sun, the Kepler 62 system offers a pair of such siblings, two worlds that may be almost entirely made of water. The inner of the two, Kepler 62e, is a super-Earth about 1.6 times the size of our planet. Its low density, however, tells a different story than solid rock. This world is so light for its size that scientists believe it is not a traditional rocky planet, but a true water world. It is likely enveloped by a global, planet-spanning ocean, hundreds of miles deep, with perhaps only a small, silicate core buried far beneath the crushing pressures of its own seas. Imagine standing on a platform, if one could exist, looking out across an endless, gentle horizon of water under a dim orange sun. There are no continents to break the waves, no mountains to catch the clouds, just a single, immense aquatic realm. The sheer depth of this ocean creates environments of staggering variety. Near the sun-warmed surface, life could harness the faint light for energy, while in the eternal darkness of the abyss, ecosystems might thrive around geothermal vents on the hidden ocean floor. This world is a monument to water, a reminder that the most vital ingredient for life might not just be present on some planets but might define them completely. Its outer sibling, Kepler 62f, presents a colder, more enigmatic possibility. Slightly smaller than Earth and orbiting further from its cool star, this world resides on the frosty frontier of the system's habitable zone. Based on the starlight it receives alone, its surface should be a frozen wasteland. Yet its potential lies in the power of an atmosphere. If Kepler 62f managed to retain a thick, insulating shroud rich in greenhouse gases like carbon dioxide, that blanket could trap enough of the star's feeble warmth to create a temperate climate. This would transform it from an icy snowball into a world with liquid water oceans, perhaps capped by polar ice but open and fluid across its midsection. The two siblings, E and F, offer a fascinating comparative study. One, the inner world, is a steamy, deep water paradise by its very composition. The other, the outer world, might achieve similar conditions through the chemistry of its air. Together, they paint a picture of a solar system not with one but two profound aquatic experiments. Could life have emerged independently in both of these global seas, or might it have begun on one and somehow traveled to the other, seeding a second ocean with the spark of biology? In the quiet light of their ancient star, these twin water worlds hold their secrets in the deep, waiting for the day we can discern the composition of their distant, moist skies. The profound depths of possible water worlds give way to a star with a more familiar golden hue. 42 light-years away, the orange K-type star HD 40307 hosts a family of planets, and its outermost known member, HD 40307G, is a super-Earth with a comfortable Earth-like rhythm. Unlike the frantic orbits of many red dwarf worlds, this planet takes its time, completing a leisurely year in about 200 Earth days. This places it squarely within the star's habitable zone, basking in a warmth that could be very similar to our own planets. But HD 40307G is a more substantial world than ours, a super-Earth with a mass several times greater. That extra heft has profound consequences. A stronger gravitational pull makes it far easier for a planet to hold onto a thick, substantial atmosphere over billions of years. This isn't a thin, wispy veil like Mars, but potentially a dense, complex shroud of gases that could effectively distribute heat from the warm equator to the cooler poles, preventing extremes and fostering a stable global climate. Furthermore, all that mass suggests a planet with tremendous internal heat from radioactive decay and the lingering energy of its formation. This heat has to go somewhere, and it likely drives a world of intense geological activity. Imagine a landscape not of quiet, ancient craters, but of towering, active volcanoes, vast rift valleys, and constant tectonic shifts. While that sounds violent, such geologic churning is a potential engine for life. It recycles crucial minerals and nutrients between the mantle, crust, and atmosphere, and can help regulate atmospheric carbon dioxide levels over eons, maintaining a temperate balance. The planet's 200-day orbit around its calm, orange sun introduces another familiar concept: seasons. As HD 40,307G travels along its elliptical path, the tilt of its axis, if it has one, would cause shifts in sunlight, creating annual cycles of warmth and coolness, wet and dry. These cycles could drive weather patterns, ocean currents, and biological rhythms, much like they do on Earth. So here is a world that feels strangely recognizable in its cadence, a place where a year has a meaningful length, where seasons might change, and where a robust, active planet provides the very geological foundations upon which life could build. It is a vision of a supercharged Earth, a planet built on a grander scale but operating on principles we understand, a potentially lush garden world orbiting a sunset-colored star. Yet a planet does not need Earth's exact warmth to nurture the green spark of life. Orbiting a star over 1,000 light-years away, Kepler 442b receives a gentle glow, about 70% of the sunlight that bathes our own world. This places it in a remarkable sweet spot, not just for liquid water, but for the very engine of most life on Earth, photosynthesis. The planet is a super-Earth, about 1/3 larger than our home, with a density that strongly suggests a rocky, solid surface beneath any potential sky. Its year is 112 Earth days long, a steady rhythm around its K-type star, a sun slightly cooler and more orange than our own. But the true significance of Kepler 442b lies in a more refined measurement, something scientists call the photosynthetically active radiation zone. This is not just about temperature, it is about the quality of the light itself. Plants on Earth have evolved to capture specific wavelengths of light, primarily in the visible spectrum, to power the chemical process that turns carbon dioxide and water into sugar and oxygen. A star must emit enough of this usable light for photosynthesis to be viable. Remarkably, Kepler 442b orbits squarely within this specialized zone for its star system. The orange-tinted sunlight reaching its surface would be rich in the red and yellow wavelengths that many terrestrial plants are exceptionally good at absorbing. If plant-like organisms evolved on this world, they would find an abundance of the very energy they need to thrive. Their leaves might not be green, as chlorophyll's color is a result of the light it reflects, not absorbs. Under an orange sun, photosynthetic life might appear in deeper shades of blue, violet, or even black to soak up every possible photon from its mellower star. This makes Kepler 442b more than a potentially habitable world. It is a world that could be visibly, vibrantly alive in a way our telescopes might one day detect. A future instrument analyzing the reflected light from this planet might not see the pale blue dot of Earth, but a different hue entirely, a tinted world whose color whispers the presence of a global biosphere turning sunlight into life. The possibility of a world perfectly tuned for photosynthesis is a powerful draw, but some of the most compelling stories in this search are wrapped in layers of mystery and debate. Just 20 light-years from Earth, orbiting the quiet red dwarf star Gliese 581, a scientific controversy captured the world's imagination. The potential planet, designated GJ581g, was announced in 2010 with electrifying implications. The data suggested a world with a mass just 3 to 4 times that of Earth, placing it firmly in the super-Earth category, and its calculated orbit put it right in the middle of the star's habitable zone. Even more intriguing, its orbital period of roughly 37 days meant it was likely tidally locked, with one face in permanent daylight and the other in endless night. Yet the temperate twilight ring between these extremes could, in theory, host liquid water and a stable climate. The lead researcher, in a moment of poetic hope, informally named it Zarmana's world after his wife. For a brief, thrilling moment, it seemed we had found an almost perfect candidate for a habitable world right in our galactic neighborhood, but the story did not end there. Other teams of astronomers analyzing the same set of radial velocity data from the star could not confirm the signal. The subtle stellar wobble attributed to planet G, they argued, was not a clear, distinct pull from another world, but likely noise in the data, a statistical artifact created by the complex interplay of the star's own activity and the confirmed signals from other planets in the system. What followed was not a simple discovery, but a profound lesson in scientific rigor. The case of GJ581G became a cornerstone debate in exoplanet science, highlighting the extreme challenges of teasing tiny planetary signals from the noisy data of faint, active stars. It forced the community to develop stricter standards for data analysis and signal validation. Yet, despite its disputed status, Zarmana's world never truly faded from public consciousness. It endures as a powerful symbol of the maybe. It represents that tantalizing point on the edge of our knowledge, a flicker in the data that could be a world of deep oceans and crimson skies, or merely a ghost in the machine. This unresolved mystery serves as a humble reminder that our map of the cosmos is still being drawn, and some of its most promising landmarks remain just out of focus, urging us to look again with better tools and sharper eyes. The debate over Zarmana's world underscores a pivotal shift in our cosmic search, a journey from simple detection to profound understanding. One world perfectly embodies this transition, a planet whose discovery sparked global headlines and whose true nature remains an alluring puzzle. Kepler 22b was among the very first worlds the Kepler telescope found orbiting comfortably within the habitable zone of a sun-like star. Announced in 2011, it was a landmark moment, proof that our spacecraft could find Earth's cousins in the temperate realms of distant suns. The data painted an inviting picture, a world about 2.4 times the size of Earth orbiting a G-type star nearly identical to our own, with a year of 290 days. The early excitement was palpable. Here was a world that could plausibly have a similar climate, similar seas, a similar story to our own. It was heralded as a potential ocean world, a new blue marble awaiting discovery. But as years passed and our tools for analysis grew sharper, the simple, hopeful story of Kepler 22b grew beautifully more complex. That crucial measurement, its size, placed it in a mysterious category between a super-Earth and a mini-Neptune. We simply do not have a world like this in our own solar system for comparison. This means its composition is a profound question mark. It could be a massive rocky planet with a dense atmosphere and deep global oceans, a true water world. Or it could be a gaseous planet with no solid surface at all, a small version of Neptune with a thick, swirling envelope of hydrogen and helium. The same starlight that reaches its orbital distance could bake a rocky surface or merely warm the upper layers of a gas giant's atmosphere. Kepler 22b thus became a foundational case study, teaching us that finding a planet in the habitable zone is only the very first step. It is not a guarantee of habitability, but an invitation to investigate. Our understanding has evolved from simply mapping the orbital sweet spot to asking intricate questions about atmospheric chemistry, internal composition, and geological activity. We now know that a planet's story is written not just by its star, but by the very stuff it is made of. Is Kepler 22b a steamy, ocean-shrouded super-Earth, or a gaseous world with hidden, ice-covered moons that might harbor life instead? This single, distant point of light holds within it the entire narrative of our quest, a reminder that the most promising addresses in the galaxy are also the most mysterious, each one a world of possibilities waiting to be unraveled. While some stars rage, others offer a quiet refuge. Only 11 light-years away, Ross 128b circles one of the gentlest red dwarfs we have ever found. This stellar calm is its greatest gift. Unlike the violent flare stars that threaten so many other promising worlds, Ross 128 is a picture of serenity, a placid ember that has shown almost no eruptive activity in years of observation. For any planet in its orbit, this means a stable, predictable environment, free from the deadly blasts of ultraviolet and X-ray radiation that can strip away atmospheres and scorch surfaces over time. The planet itself is a compelling find, an Earth-sized world with at least 1.35 times our planet's mass, almost certainly a rocky body like our own. It hugs its star closely, completing an orbit in just under 10 Earth days, a proximity that almost certainly locks one face in permanent daylight and the other in endless night. Yet this tidal locking, often seen as a challenge, may not be the obstacle we once thought. Advanced climate models for Ross 128b reveal a fascinating possibility. If this world possesses an atmosphere with a composition and pressure similar to Earth's, that atmosphere would act as a global heating system. Winds and ocean currents, if oceans exist, would efficiently transport warmth from the scorching dayside across the entire planet, dramatically warming the frigid night hemisphere. The result could be a vast, temperate region, particularly in the areas along the twilight zone, where liquid water could pool and persist, without the constant threat of stellar tantrums to blow its protective shroud away. Ross 128b has had a much better chance of holding onto that crucial atmosphere over billions of years. It stands as a quiet, nearby sanctuary, a world whose potential is not in dramatic extremes but in profound stability. In the search for life, a calm star may be the most precious neighbor of all. The calm stability of a quiet star is a precious asset, but habitability can also be a delicate balancing act. Orbiting the orange dwarf star HD 855112, just 36 light-years away, is a super-Earth that lives on the very edge of possibility. HD 855112b is a world with a mass about 3.5 times that of Earth, and its discovery in 2011 sent a wave of excitement through the scientific community. Found using the radial velocity method, which detects the subtle wobble of a star tugged by an unseen planet's gravity, this world was immediately recognized as something special. Its orbit placed it right on the inner, warmer boundary of its star's habitable zone. Early climate models presented a fascinating conditional scenario. For this super-Earth to avoid becoming a scorching Venus-like hellscape, it would need a very specific kind of global thermostat clouds. The calculations suggested that if at least 50% of HD 855112b's daytime sky were consistently covered by reflective clouds, those clouds could bounce enough of the star's intense heat back into space to cool the surface to a temperate, Earth-like range. This introduced a powerful concept in planetary science, albedo, which is simply a measure of how much light a surface reflects. A planet's albedo is its built-in climate control. Earth's average albedo is about 30% thanks to its white clouds, ice caps, and oceans. A world like HD 855112b, living so close to its sun, would need to be even shinier. Those hypothetical clouds would likely be made of water vapor, just like ours, creating a stabilizing feedback loop where more heat leads to more evaporation, which forms more reflective clouds, which then reduces the heat. It is a delicate dance between star, sea, and sky. Beyond its own story, HD 855112b played a pivotal historical role. In the early days of exoplanet hunting, the discovery of a rocky world in the habitable zone of a sun-like star was still a rare event. When astronomers included it in their statistical models, It helped form some of the first educated guesses about just how many potentially habitable planets might be scattered across the Milky Way. Those early estimates suggesting tens of billions were shaped by worlds like this one. So while later studies have debated its actual cloud cover and climate, HD 855112b remains a landmark. It taught us that a planet's potential is not just about where it orbits, but how it manages the light it receives, using its own atmosphere as a brilliant, reflective shield to carve out a home in the heat. The search for a world that feels truly familiar often leads back to stars like our own. Kepler 1638b is a testament to this quest, a planet discovered by the Kepler telescope orbiting a G-type yellow dwarf star, a stellar twin to our Sun. While red dwarfs are abundant and their habitable zones easier to probe, finding an Earth-sized planet in the temperate region of a Sun-like star is a rarer and more significant prize. Kepler 1638b delivers on that promise, a world with a radius just 1.2 times that of Earth, making it a near-perfect match in size. Its orbit, however, is where the sense of familiarity deepens. This planet takes its time, completing a full journey around its star in 259 days, a year remarkably close to our own 365-day cycle. This orbital rhythm places it comfortably within the star's habitable zone, bathing it in a level of sunlight comparable to what Earth receives. The implications are profound. A G-type star like this one offers a stable, long-lived source of energy, burning steadily for billions of years without the violent flares common to smaller red dwarfs. This stellar calm provides a consistent environment, a steady hand on the planetary thermostat that could allow for the gradual, patient evolution of complex chemistry and potentially biology. Kepler 1638b suggests that the specific conditions that nurtured life on Earth, a rocky world of a certain size, orbiting at a certain distance from a certain type of star, are not a singular cosmic accident. They are a recipe that the universe appears to have followed more than once. It is a quiet affirmation that pale blue dots may circle yellow suns throughout the galaxy, each with its own story of dawns, seasons, and perhaps oceans whispering under an alien sky. But our closest stellar neighbor still had secrets to reveal. Proxima Centauri, the star that hosts the potential world Proxima b, also holds a third, far lighter companion, Proxima Centauri d. Confirmed in 2022, this tiny world completes an orbit in just 5 Earth days, skimming so close to its faint red sun that its year is a fleeting blur. Its most astonishing feature is its mass, a mere quarter of Earth's, making it one of the lightest exoplanets ever detected around a sun-like star. This presents a fundamental puzzle for planetary science. A world this small and this close to its star faces immense challenges. The stellar wind and radiation from Proxima Centauri are relentless, and with such weak gravity, holding onto any substantial atmosphere would be a constant struggle. Over billions of years, the air around Proxima d may have been stripped away entirely, leaving a barren, airless rock bathed in harsh light. Yet, the very existence of this diminutive world expands our understanding of what planetary systems can look like. Here, just 4.2 light-years away, we have a compact family of at least 3 worlds, each telling a different story. Proxima b is the Earth mass candidate in the habitable zone, a world of profound maybe. Proxima c, a more distant and colder super-Earth, hints at the system's outer reaches. And now Proxima d, a tiny, swift world of rock, shows us that even the smallest of planetary seeds can form and endure in the violent environment of a red dwarf. This triple system, our immediate cosmic backyard, is a miniature laboratory. It shows that a single star can host a diverse collection of worlds, from potential water-bearing havens to small, scorched siblings. The discovery of Proxima d reminds us that planetary formation is a prolific process, capable of building not just giants and twins, but also the delicate, miniature worlds that complete the family portrait. A planet's density can whisper the secret of its composition. Orbiting a binary star system 100 light-years away, TOI 1452b is a super-Earth that speaks in the language of water. Data from the TESS satellite and follow-up observations reveal a world about 70% larger than our own, but with a mass only 5 times greater. That math is the key. Its surprisingly low density cannot be explained by a ball of rock and metal alone. Instead, the numbers point to a planet made of something far lighter, a material that could make up as much as 30% of its total mass. That material, scientists believe, is almost certainly water. This is not a world with lakes and seas scattered across a rocky crust. TOI 1452b is likely a true ocean planet, a global water world whose entire surface is a single, uninterrupted sea, hundreds of miles deep. Picture a horizon with no land in sight, under the gentle light of 2 distant suns. The sheer weight of this planet-spanning ocean would create pressures at the bottom so immense that the water itself might be compressed into exotic forms of high-pressure ice, forming a strange, solid mantle above a small, rocky core. Yet in the sunlit upper layers and the vast, dark middle depths, a global aquatic environment of liquid water could persist. This is an environment utterly alien to our terrestrial experience, a planet with no mountains, no continents, no beaches, only the endless, gentle swell of a deep alien sea. For life, however, such a world is not a prison but a potential paradise of immense volume. In the perpetual darkness of its abyss, far from the faint warmth of its binary stars, ecosystems could thrive around geothermal vents on the submerged seafloor, powered by the planet's internal heat. Simple microbes could flourish, and over eons, perhaps more complex organisms could evolve to navigate the eternal currents of this global ocean. It is a reminder that the most vital ingredient for life might not just be present on some worlds, but might define them completely, creating a hidden, liquid universe beneath a steamy sky. Stability is the ultimate gift a star can offer its planets. 100 light-years away, a world named LP 899c orbits a star so faint and cool it is barely visible to our telescopes. Discovered by a project with the fitting name Speculoos, which scans the skies for planets around these dim, ultra-cool dwarf stars, this super-Earth is a masterclass in cosmic patience. The star itself is a slow-burning ember, a type of red dwarf that emits a gentle, deep red glow and almost none of the violent flares that plague its more active cousins. This tranquility means the space around it is a calm harbor, bathed in low levels of harmful radiation. For any orbiting world, this is an environment of profound stability, one that could persist not for millions, but for trillions of years, far longer than the current age of the universe itself. Within this enduring twilight, LP 899c has found a perfect seat. Roughly 40% larger than Earth, it is almost certainly a rocky world, and its orbit places it squarely in the middle of what astronomers call the conservative habitable zone. This is the most optimistic calculation for liquid water, a zone where a planet with an Earth-like atmosphere could easily maintain oceans on its surface. The gentle, consistent warmth from its ancient star could foster a climate of remarkable steadiness, free from the stellar tantrums that might strip away a protective atmosphere or scorch a nascent biosphere. This discovery underscores a pivotal shift in the hunt for life. While we once focused on stars like our Sun, we now recognize that these small, quiet, ultra-cool dwarfs are exceptional havens. They are the most common stars in the galaxy, and their dimness makes it easier for our instruments to detect the tiny shadows of Earth-sized planets crossing their faces. Their longevity offers biology an almost unimaginable span of time to begin, to experiment, and to complexify. A world like LP 899c is not just a candidate for life, it is a candidate for ancient, deeply rooted life, a potential garden that has been quietly cultivating its secrets under a perpetual crimson sun for longer than our solar system has even existed. The quiet stability of a long-lived star shows how durable a habitable environment can be, but how far can that concept truly stretch? At the very outer frontier of possibility, a world like Kepler 1652b challenges our most basic assumptions about where life can exist. This Earth-sized planet orbits a red dwarf star, but its position is so distant that it receives even less sunlight than Mars does in our own solar system. By our traditional, sunlight-centric standards, this should be a frozen, lifeless snowball, a world locked in permanent ice. Yet planetary science reveals a more nuanced truth. The habitable zone is not a fixed line, but a flexible boundary shaped by a planet's own atmosphere. Kepler 1652b could defy its icy fate if it possesses a very specific kind of atmospheric blanket, one rich in powerful greenhouse gases like hydrogen. Hydrogen is a remarkably efficient insulator, far more potent than the carbon dioxide in Earth's air. A thick shroud of hydrogen gas could trap enough of the star's feeble infrared warmth to create a significant greenhouse effect, raising surface temperatures by tens or even hundreds of degrees. This could transform a world that should be colder than Mars into a temperate, potentially watery planet, a place where global oceans might persist under a perpetual, deep red twilight. This possibility forces us to expand our definition of habitable. We can no longer search only for planets with Earth-like atmospheres of nitrogen and oxygen. We must now consider the vast spectrum of atmospheric chemistries that other worlds might possess, from the hydrogen-dominated skies of Hycean planets to the carbon dioxide-rich air of a super-Earth. A planet's potential is not written solely by its star, but in the complex interplay between the light it receives and the chemical cocktail it retains. Kepler 1652b stands as a testament to this expanded vision, a reminder that the cosmic conditions for liquid water and perhaps life may exist in the most unexpected places, on worlds that keep themselves warm from the inside out with atmospheres utterly alien to our own. 16 light-years is a cosmic stone's throw away, and there, orbiting a star so quiet it barely whispers, we find another pair of Earth's potential siblings. The star is GJ 1002, a red dwarf of exceptional calm, and circling it are two rocky worlds almost exactly the mass of our own planet. This is the GJ 1002 system, and its two planets B and C represent a new benchmark in the search for nearby temperate Earths. The inner world, GJ 1002b, sits on the warmer, inner edge of the star's habitable zone. Its year is a rapid 10 Earth days, a tight orbit that bathes it in more of the star's gentle crimson light. This position suggests a world that could be warm, perhaps even tropical, if it possesses an atmosphere. However, living on the inner edge is a delicate balance. Without sufficient cloud cover to reflect some heat or the right atmospheric composition, such a world risks tipping into a runaway greenhouse state, becoming a steamy, Venus-like oven. Yet, its Earth-like mass is a powerful argument for a solid, rocky surface, a foundation upon which oceans could theoretically pool. Its sibling, GJ 1002c, offers a more classically temperate prospect. Orbiting further out in a 21-day year, this planet resides in the very heart of the system's habitable zone. The amount of stellar energy it receives is remarkably similar to what Earth gets from our Sun. This placement makes it a prime candidate for a stable, Earth-like climate, assuming it has the atmospheric blanket to match. The profound significance of this duo lies not just in their perfect size or promising orbits, but in their combined context. Their host star's profound inactivity means these planets have been spared the atmospheric stripping flares that ravage other red dwarf systems. They have likely enjoyed billions of years of environmental stability, a long, quiet chance for chemistry to become biology. Furthermore, their proximity and the star's dimness create an ideal scenario for the next great leap in exoplanet science. When the next generation of giant ground-based telescopes, like the extremely large telescope, turns its gaze toward GJ 1002, it will have a clear shot. Astronomers will attempt to capture the light of these planets directly, separating their faint glow from the stars, and then split that light into a spectrum. That rainbow will hold the chemical fingerprints of their atmospheres. They will search for the telltale dip of water vapor, the signature of methane, and the potential electrifying spike of oxygen. Finding oxygen alongside methane on a rocky world like JJ1002c would be a revelation, a combination that on Earth is maintained almost entirely by life. This nearby, quiet system offers two for the price of one, a double opportunity to answer the oldest question: are we alone in a silent cosmos, or is life a common whisper between the stars? So we have journeyed past 30 distant shores, each with its own promise and puzzle. Yet as we reach the end of this catalogue, a fundamental truth emerges. There is no single winner in this cosmic contest, no one perfect world that holds every key to life. Instead, we have discovered a portfolio of possibilities, a gallery of planetary prototypes, each showcasing a different strength. Some, like Wolf 1069b, are perfect Earth mass twins. Others, like Kepler 452b, orbit the comforting glow of a sun-like star. A few, like K218b, have already whispered to us of water vapor in their alien air, and a handful, like Proxima Centauri b, are tantalizingly close, mere interstellar neighbors in the vast cosmic dark. If we could dream, if we could combine the very best traits from across this list into one ultimate world, what would that dream team look like? Let us imagine the ultimate habitable exoplanet. We would start with the proximity of Proxima b, placing our world a mere 4.2 light-years away, a stone's throw on the galactic scale, close enough for our telescopes to study in intimate detail and for future generations to dream of reaching. We would give it the perfect size and temperate position of TRAPPIST 1e, a rocky body nestled in the heart of its star's habitable zone with the potential for Earth-like oceans and continents. We would bless it with the confirmed water-rich atmosphere of K218b, a sky thick with the vapor of global seas, a definitive sign that the most crucial ingredient is present and abundant. And finally, we would place it all under the stable, golden light of a star like Kepler 452's, a sun-like G-type dwarf offering billions of years of consistent, gentle warmth without the violent flares of a red dwarf. This fantasy world does not exist, of course, but its separate pieces do, scattered like jewels across the galaxy, and that is the real revelation. The universe is not building one kind of home, it is experimenting with countless blueprints. Our search is not for a duplicate of Earth, but for understanding the full spectrum of places where life could take root, from the deep, dark oceans of Hycean worlds to the twilight rings of tidally locked planets. The ultimate candidate is not a single point of light, but the collective answer written in the atmospheres of dozens. Each world on this list, from the ancient quiet of Teegarden Star B to the stormy potential of a mini Neptune like K218b, adds a crucial piece to the puzzle. Together, they tell us that the conditions for life are not rare or fragile, but woven into the fabric of the cosmos in a stunning variety of ways. The question is no longer if such worlds exist, but which of them will be the first to send us a signal, a chemical signature in the starlight that changes our story forever. The ultimate candidate is not a single world, but a question we are now poised to answer. This grand catalogue of 30 possibilities has set the stage, but the next act is already unfolding, driven by a golden eye in the dark. The James Webb Space Telescope is no longer a promise, it is a working instrument, and its gaze is fixed on worlds like K218b and the TRAPPIST-1 planets. Its mission is not to take pretty pictures, but to perform a kind of cosmic chemistry. As each planet passes in front of its star, a sliver of starlight filters through its atmosphere. Webb captures that light and splits it into a spectrum, a chemical barcode. Scientists then scour that data for the faint fingerprints of specific molecules. They are hunting for biosignatures, gases that, in the right combination, strongly suggest biological activity. Oxygen in large quantities is a key target, as on Earth it is primarily replenished by plants and phytoplankton. Methane is another, especially when found alongside oxygen, a combination that quickly destroys itself unless something is constantly producing it. And then there is the more exotic whisper, dimethyl sulfide. On our planet, this gas is only produced in massive amounts by marine life. Detecting it in the atmosphere of a Hycean world like K218b would send an electrifying message, a hint that something is thriving in that global, sunless ocean. These are not distant dreams, but active analyses happening right now. Every new observation from Webb adds a data point, refining our understanding of which of these 30 worlds are truly draped in life-friendly air. But Webb is just the beginning. Looking further ahead, missions now on the drawing board aim to accomplish what once seemed pure science fiction. Concepts like the Habitable Worlds Observatory envision a space telescope so powerful it could directly block out the light of a star and capture the faint reflected glow of a small, rocky planet orbiting within its habitable zone. We would see it not as a point but as a pixel, a pale dot. And by analyzing the colors and spectra of that single pixel of light, we could map its surface, searching for the glint of oceans, the green hue of continents, or the seasonal changes of a global biosphere. This is the tangible future of the search. The catalog we have built is the target list. The tools we are building are the keys. For the first time in human history, the detection of life beyond Earth is not a philosophical question, but a technical challenge with a plausible timeline. It means the moment of discovery, that staggering revelation that we are not alone in the cosmos, could very well happen within our lifetimes. The data that changes everything might already be traveling toward us as starlight, filtered through an alien sky, waiting for the right instrument and the right moment to be read. Our journey across 30 worlds reveals a cosmos not of barren rocks and gas giants, but of profound and stunning variety. We have charted the deep, global oceans of water worlds like TOI 1452b and peered into the steamy, hydrogen-shrouded skies of Hycean planets like K218b. We have found rocky twins of Earth, from the quiet stability of Wolf 1069b to the sunlit familiarity of Kepler 1638b, orbiting stars that range from violent red dwarfs to serene, ancient embers and golden suns like our own. This is not a catalogue of similarities, but a testament to nature's boundless imagination. The galaxy is not a desert sprinkled with a few rare oases. It is a vibrant, sprawling metropolis of potential habitability, where the conditions for liquid water and life are crafted in countless different ways. The sheer number of candidates and the sheer diversity of their designs tells us one thing with growing certainty. The universe is likely teeming with real estate that could cradle biology. So the next time you find yourself under a clear night sky, look up, pick a star, any star. It might be a faint red pinprick or a brilliant golden beacon. And know this, around that star there could be a world with a global sea under a crimson twilight, or a planet where 3 suns set over alien mountains, or a deep, dark ocean hidden beneath a shell of ice. On one of those distant shores, the chemistry of life may have already sparked, evolved, and perhaps even gazed upward, wondering if it too is alone in the silent dark. The search is just beginning, and every new discovery brings us closer to the answer. Which of these 30 worlds feels most like a home to you? Share your thoughts in the comments below. If you want to join us on the next cosmic journey, subscribe now. The universe still has countless stories left to tell.